We need to spend a little time talking about acids and bases, because what we're going to do is take all of that information that we learned about equilibria, our ICE tables, what an equilibrium constant expression is, about heterogeneous versus homogeneous mixtures, all of that information from the previous chapter, learn about acids and bases, and merge them together in this series. So what we have in a picture here is actually in our textbook, it's a sinkhole. Limestone, which is a carbonate, will easily react with acid. Now, even rainwater is slightly acidic, so the groundwater will hit that limestone and you'll have an acid-base reaction which will dissolve the carbonate and cause our caving system that we see here in Kentucky. And here is an image of a sinkhole filled up with water. Okay, so let's talk about acids and bases. As you go back into history and they start studying stuff, one of the things they like to do is taste it, see what it tastes like, okay? So we've got properties of acids, and it starts with, hey, it tastes sour. So anything that tastes sour to us is an acid. Now, I don't want you going into the laboratory and tasting the acids, but let's think of sour things that we're familiar with. There's a picture of a lemon there. Lemons and your citric fruits have a sour taste to them. They have an acid. We call it citric acid, okay? But any acid will have that sour taste to us. They can dissolve many metals. Not all metals, but many metals are dissolvable into acidic solutions. They can change the color of plant dyes. So these are things that they're observing. One of the things I used to like to do when I had small classes and when I'd go do demonstrations with kids is take red cabbage and boil it and take the liquid off of it. It's purple color, and you can add different acids and bases, and it will change a wide variety of colors. And that's what litmus paper is based off on, that concept of what is it in those plant dyes that change colors, and they utilize that because depending on how these acids are, they will have different colors on those plant dyes. And then the last thing they notice is, well, they neutralize bases. If you put them in with bases, they take those base properties away. Okay, so what properties did they notice that bases had? Okay, the first one, let's taste it, okay? It tastes bitter. If you've ever had your mouth washed out with soap, which I hope you haven't, or maybe you just have a curious mind and you want to stick it to your tongue, you're going to see that it's very bitter tasting. Bases are all bitter in their taste. Again, don't go tasting the bases in the chemistry laboratory. They're also slippery. Soap is slippery from that base property, okay? But if you're in the lab and you happen, which I hope you don't do this because you've got gloves on your hands, but maybe you get them on your gloves and there is a slipperiness to bases. Well, and they will neutralize your acids and take the acid properties out. So these were the observable things. We observed them on the large scale, not the molecular scale, but the scale that we can taste and feel, okay? But let's define acids. Now, we did define acids in a much more previous chapter according to what's called the Arrhenius Definition. There are basically 3 definitions, and it says that we will learn, and as I'm thinking through my notes, I think we took one of them out, okay? But the Arrhenius definition is a very limited definition. It's not that each definition is a better and better definition. It's just that they are different levels of scope of magnitude. The Arrhenius definition is very limited. You can only define an acid and a base with how it behaves when it's in water. Now, very often acids and bases are in water, so that's a handy definition, but it is limited compared to some of our other definitions. The Bronsted-Lowry definition is the vast, that says vast majority. It's supposed to be vast majority. I can't believe I've used these notes over and over again and never noticed that. The vast majority of our discussion in this chapter is going to be centered around the Bronsted-Lowry definition. And then the last definition is the Lewis definition. Now, when you think back to Lewis structures, what did we put around our structures with these dots? What did those dots represent? They represented electrons. So the Lewis definition focuses on what the electrons are doing. Now, when you I don't know that we won't focus on that definition in this chapter, but when you deal with various reactions, you'll see that playing out in some of your future work in chemistry if you take other chemistry classes. So let's go back to the Arrhenius definition, which was defined for us before. What's an acid? A substance that produces H+ ions in aqueous solution. So if you take the substance and put it into water, you end up generating H+ ions. So an example, HBr, is an acid by this definition. When you take HBr and you put it into water, okay, I'll just write water above the arrow. I'm plopping this, and it's actually a gas. So I'm dissolving it in water. What you end up doing is it breaks apart into H+ ions that are dissolved in the water and Br- ions that are dissolved in the water. Okay, so we have produced H+ ions, so that meets the definition of an Arrhenius acid. Now, what is a Arrhenius base? Arrhenius base would be a substance that, when you put it in water, produces OH- ions. So here's an example. All your metal hydroxides would fit this category. So this is an example of KOH. It's a solid. When you put it into water, it will break apart into K+ ions that are dissolved in water and OH- ions that are dissolved in water. So that meets the definition of an Arrhenius base. Now I'm going to show you another definition which is not as obvious. If you have a metal hydroxide, it's an ionic compound, we'd expect it to break apart, being a strong electrolyte as ionic compounds are. And if it's soluble, great, you're going to end up with a lot of ions in that solution. But if I were to look at this guy, ammonia, and I were to put it into water, there's no OH minuses in there, but here's what happens. And I'm going to use a reversible arrow because this is actually an equilibrium, not go directly all to products. The NH3 pulls off a hydrogen off of this, and it turns into NH4+. It doesn't just pull off a hydrogen, it pulls off an H+ off of this. And what is water left with? OH-. Okay, so it's a substance that produces OH- when you dissolve it in water. It didn't have the OHs, but it produced it by pulling a hydrogen off the water. So by that means, it fits the definition of an Arrhenius base. So in the Arrhenius definition, it's about what's produced. If it's an acid, it produces H+ ions when it dissolves in water. If it's a base, it produces OH- ions when it dissolves in water. So it's limited because water has to be in there. Okay, let's go to the next definition. It's broader. It does not require the water. Now, all of our definition of an Arrhenius acid and base will fit into this more inclusive definition. So it'll still meet the definitions in the right way from here, but it doesn't have to have water, so it's a little bit broader. Acids are defined as proton donors. Now when you think proton donor, you might be thinking of a nuclear particle, and when I'm thinking acids and bases, I'm never thinking that, because what I'm thinking of is H+. All right? H+ is a proton. Why in the world would I call that a proton? Well, let's think of a hydrogen atom. Hydrogen atom has a proton in the nucleus, okay, and then it has one electron buzzing around in the 1s orbital. That is a hydrogen atom. Okay? It might have some neutrons in there, but not usually. The vast majority of them are simply this. Now, what happens if I remove that electron? If I remove an electron from something that's neutral, I end up with the H+ ion. If I remove that electron, what is sitting there? Simply a proton. So when I say proton donor, by the acid definition here, I'm thinking in my mind H+ donor. Okay? So does this meet the definition of a Bronsted-Lowry acid? Is it a proton donor? Well, yes, it donated its proton, and we were left with the Br behind. All right, so that would meet the definition of a proton donor. Let's look at this water molecule. Does it meet the definition of a proton donor? Did it not give its proton to here? And that made the water in this case an acid. Okay, the water is an acid, whereas this is a base. By the definition, a base is a proton acceptor. If we look at this example, we had this guy being a base because it increased the OH minus ions in water. But is it also a proton acceptor? Did it accept a proton from the water to become NH4 plus, keeping in mind that a proton is an H plus? If you take this and put an H plus on it, you're left with that. One more H, and the plus comes along for the ride. Now, that's the definition, proton donor, proton acceptor. I keep in my mind, in order to keep all this straight, an acid, hydrochloric acid or hydrobromic acid. I have that in my mind. Proton donor, it's going to donate, okay? So then proton acceptor is its opposite. Now there's a couple terms here that we're going to make sure we get familiar with, and that's got the word conjugate with it. Conjugate base is the species that remains after the acid has donated its proton, okay? And the conjugate acid is the species that is formed when a base accepts a proton, okay? So it is, we could say formed or remained. We'll get a good feel for this. I'm just now noticing I'm using one as what remains and what's formed. It's simply the same idea. Let's look at this example, all right? CH3COOH plus water. As you look at this, and I'm going to go over to the screen and actually write on the screen here. You want to compare things that look similar. And you want to look at them and say, what's the difference between them, and find it. There it is. Now, as this guy became, the guy on the right, as this became this, what did it do? It donated a proton, right? Where did it donate it to? It gave it to the water. If I look at the water here versus what it becomes over here, we see that this accepted it. So if this donated an H+, it must be the acid, because a proton donor is an acid. What did it become? What remains after it donates? Well, this is its conjugate base. So they're paired together. Water accepted that proton, right? Now I said it donated, I'm saying it donated to become this, but who did it really donate to? It donated to the water. So the water accepted that, and a proton acceptor is a base. So in this case, water is a base. Now what did the base become after it accepted the proton? It became this guy, which is the conjugate acid. So conjugate acid-base pairs are matched up, as you see here, okay? Those are the conjugate acid-base pairs. So that's language we have to get familiar with as we go through it. Let's go back to this light board and let's look at my ammonia example up here. And let's do a similar argument. This is what we have, and we see that it pairs up with this guy over here, right? So ammonia, what did it do to become this guy? Well, here he has one more H+. So to go from here to here, it must have accepted a proton. Who did it accept it from? From the water. The water gave it, okay? If it's a proton acceptor, it's a base. If it's a proton donor, it's an acid. So in this example, we see water acting as an acid. Over there, water was acting like a base. Now we come over to the right-hand side and we pair it up. If this is the base, what it becomes is what? It's the conjugate acid. Okay, get this out of the way. This is the pairing. The water pairs up with the OH. If this is the acid, this is its conjugate what? Base. Okay, so we pair them up. Whenever you have an acid-base reaction by the Bronsted-Lowry definition, and you'll see some books that will get rid of the Lowry. Poor Lowry gets left out. They'll just call it Bronsted acids and bases. But the people who are all-inclusive are going to call it a Bronsted-Lowry, and those of us that get lazy might call it a Bronsted acid, but that's the same deal, okay? Whenever you're defining it this way, it is a transfer of an H+ from one guy to the other, and every time you do this, you have the pairing of what it is and what it becomes. Okay, we won't worry about all that because it's the same thing I had written down there. Just driving this whole notion home, okay? And whenever you have a conjugate acid-base pair, they are only going to differ by a single H+. Okay? So on the left, I have ammonia and its conjugate acid. On the right, I have water and its conjugate base. That's what we had represented right up here on this board. You would never have something like this. H3O+, H3PO4, that is phosphoric acid, and PO4, 3-. Those are not conjugate acid-base pairs. They are differing more than just one H+. They're differing by 3 H+. So these do not pair together. What would be this guy's conjugate base? If this is an acid and a proton donor, what would be its conjugate base? We'll take an H+ off of it, and you would have only 2 hydrogens. And what would its charge be? You took a plus away from something that was neutral, so this is minus charge. These are the conjugate acid and the base pair. Okay, we call this conjugate acid-base pair. This is the acid, this is its conjugate base. Or this is the base and this is its conjugate acid. That's the way we talk about those things. Okay, so we're going to go through some examples and let you answer some questions about this. What are the conjugate acid-base pairs in the following reactions? Notice here, there is no water involved. I told you that this is a more inclusive definition of acids and bases. The Arrhenius definition would not hold in this because we don't have anything that is producing H+ ions and OH- ions in water. But we are defining them by the proton transfer. Okay, so you find the conjugate acid, the acid on the left-hand side. Which one of those is the acid and which one is the base? Oh, I get it right. Oh, I thought it was just going to pop up. Let's get my pen and let's write on the screen there. Hopefully you've already answered it. Okay, this has got the H on there, and over here it no longer has the H, so it donated it. This is the acid. This is its conjugate base. Conjugate base is his partner on the product side. Now if this is the acid, the H+ was donated over here to this guy because we noticed that it picked up that hydrogen to become to have more hydrogens over there. Okay, so this is the acceptor. Okay, this would be the base. He is the proton acceptor. What he becomes after he accepts the proton is the conjugate acid. Now notice this is a reversible reaction, so this reaction can go in both directions. The acid would donate to the base and form the stuff that we see on the right-hand side. So it goes in both directions. Now let's try another one. I'm going to erase these out of the way. You rewind it and stare at it if you need to get that information down. Let's look at this one. I want you to find the acid that sits on the left-hand side, the product side of this reaction. Well, that got carried away, didn't it? Try that again. All right, find the acid over here. All right, what is the acid? This is the acid. Why do I know it's the acid? Because it donated a proton to become OH-. All right, so that makes this the base. Now look at the product side. Which one of those is the conjugate acid? The conjugate acid is tied to that base there. Okay, let me get that out of the way. Boop, there we go. There's the base, so here's its conjugate acid. They only differ by an H+. And here is the acid, so this is its conjugate base. All right, we get the idea there. I want you to note up here, well, I guess I better write them down. This is the acid, this is the base, because the acid donated to the base to become this conjugate base and this conjugate acid. Okay, now I am seeing H3O plus written here, and this is an important thing to note, because if you go and look at websites and you go look at textbooks and you start noticing things, you're going to see that sometimes you'll see the H3O plus written and sometimes you will see it not written. That third reaction you see right there, I wrote it as a acid-base reaction where we have the proton being swapped between the acid and the base. Sometimes you will see this reaction written this way, where it's just breaking apart into ions. The HNO2 in water does this. So this fits the definition of the Bronsted-Lowry acid-base, okay, acid-base reaction, but it also fits the definition of the Arrhenius definition. Oh, I don't know why that thing keeps giving me too much information. All right, this fits the Bronsted-Lowry definition here, but it also fits the Arrhenius definition because water is included. I typically do not, I'll just put a frowny face. I do not use it in this form, typically. There's nothing wrong with it. But it's hard for me to see this as a H plus swap, a proton swap, because I'm not seeing that hydrogen being donated to anything. So I like to keep this Bronsted-Lowry look and not write it this way and lose the water, which is the proton acceptor. Another thing that we see here is sometimes water acts as an acid and sometimes it acts as a base. Let me do a little erasing up here of a lot of extra, well no, let's not. Let's look at the water and these two reactions, okay? I'll put a big box around where I want you to look. In this reaction that I'll call number 1, it's acting as an acid. In the reaction that I'll call number 2, it's acting as a base. In number 1, it's donating a proton. In number 2, it's accepting a proton. The word we use for that is amphoteric. Amphoteric is a substance that can act as an acid or act as a base depending upon its environment and depending upon the battle of the H. So what we're going to do is we're going to look at water a little bit more closely in the next lesson. Water can act as an acid and can act as a base, and it will actually do that ionization process with each other, okay? Where one molecule acts as an acid and the other one acts as a base right there within the same reaction chamber. So that's what we will look at really closely as we move forward, because that equilibrium will come into play every single time you're in an aqueous solution.